Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Good morning, good afternoon, and good evening from me as well. I am Guilherme Martinez-Rohrer from the International Telecommunication Union, and it's my pleasure to welcome you all for today's AI for Good Discovery event on Robotic Foundations models organized by the ITU. In this session, we will explore how large neural network models, similar to those behind AI assistants, coding tools, and chatbots can enable general robotic skills. We will look at how these models can combine semantic knowledge from web-scale pretraining with physical understanding from robot data, leading to breakthroughs in robot control and adaptability. This event is part of the AI and Robotics Discovery Series, which features expert talks on cutting-edge research and innovations in autonomous and intelligent systems, helping us understand how AI and robotics can address some of the humanity's biggest challenges. And we are delighted to have a very distinguished speaker here with us today. And as always, we count on your participation to make this an interactive and engaging session. As a reminder, you can share your questions in the AI for Good neural network chat room, and we will address them during the Q&A. So without further ado, it is my pleasure to introduce our speaker today. He is Professor Sergey Levine, Associate Professor at the University of California, Berkeley. Sergey, the floor is all yours.
Great, thank you. All right, so today I'm going to talk about robotic foundation models. To set the stage a little bit, I'm sure all of you are familiar with the capabilities that large language models have enabled in terms of tools that we can all use, AI assistants, tools for programming, tools for web search, and more. And maybe you've sometimes wondered if you can ask large language models to do the sorts of things that you would like done around the house. Maybe you can ask it to clean the house, fold the laundry, and make dinner. When you ask Gemini this question, this is what it tells you. It sounds like you have a busy evening ahead. Of course, because large language models are not embodied systems. They are virtual assistants at best, and they can only control virtual things. But wouldn't it be nice if we could have that same kind of general purpose capabilities in physical systems and robots, so that you could ask a robot, clean the house, fold the laundry, and make dinner, and the robot would actually go and do it. So about 1.5 years ago, we set out to create these kinds of systems at my company, Physical Intelligence, building on years of prior research that we had done, both academically and in industry. We were able to get pretty far. So this is a video of one of our early prototypes. This is about 1 year ago. This is a robot that is using an end-to-end trained neural network policy to take laundry out of a dryer, put it into a basket, and then fold it. And here it'll be sped up a little bit so you can see the process. Takes out all the laundry, picks up the basket, and this is all controlled end-to-end with a single neural network. There isn't any kind of hand-designed traditional planning algorithm underneath this. It's essentially a generalization of the kind of technology that we've seen behind large language models. And if I let this video play for maybe another 15 minutes, you'll see it folding all laundry items. I won't go through the whole thing right now. But more recently, we've generalized these kinds of methods to a variety of other tasks. Here you can see a more advanced version of the same system, cleaning up a kitchen, putting away items, putting dirty dishes into a sink, things like that. And the principles behind these technologies, of course, are a bit more advanced than language models because they have to process observations and physical controls. But broadly speaking, they're based on the same foundations. machine learning with large data sets and very large high-capacity transformer models. Okay, now these kinds of ideas go beyond just robots to clean your home, and there's a bigger picture problem that is being solved here. The problem is that robotics, in its physical form, has the potential to really transform many different sectors of the economy and of our lives. It can automate logistics, tasks in the home, agriculture, medicine. There are lots of things that people do with their hands that could be done by machines. There are many more things that people don't do with their hands because these are not things that are either economically viable or where there's sufficient labor to get them done that could be done with robots, taking care of the elderly, all sorts of other tasks. The problem with broad deployment of robotic systems so far has been that if you want to truly solve a robotic application, you typically need to build an entire R&D effort around it, and probably on top of that, an entire productization effort. So each of these robotic applications is itself a massive undertaking, the way that these things have been handled in the past. There are many things that go into this, making hardware, developing custom software, programming all the movements of the system, designing the appropriate motion planners, safety mechanisms, and so on. So this has been tremendously challenging, and this is why, although we've had the technology to build robotic hardware to do all these things for decades, the deployments of these kinds of robots in the real world have not yet occurred. So the big question that I'm going to talk about in this talk is, can we build a general purpose brain that can enable any robot to do any task? Because if we could do this, then many of these applications that physically have been possible for a long time would actually be feasible to do. And in fact, they could be feasible to do with the same basic software platform. So the main idea is to develop the technology that enables a generalist policy trained on many different tasks and many different robots to then generalize to the kinds of downstream applications that we might want it to do. And the reason I started this talk by talking about large language models is that at its core, this idea closely parallels what large language models have enabled for natural language. So it used to be that in natural language processing, we would also have to build very different, very bespoke technology for each application of NLP. If you want to do machine translation, you would have to build an entire technology stack around machine translation. If you wanted to do summarization, you would build an entire technology stack around summarization. But now, large language models provide generalist natural language processing capability and therefore can tackle all of those domains with the same underlying technology. So the parallel here is perhaps the same kind of blessing of generality can enable broad application of robotic technology if we could figure out how to build robotic foundation models. So there are three key challenges that we need to discuss to understand how to do this. The first is what kind of machine learning system can actually learn physical skills. So what are the actual models underlying this? And this is what academic researchers spend perhaps the bulk of their time thinking about. But there are other very important questions. For example, the data. What do we actually train these systems on? That is absolutely critical for the performance of robotic foundation models and is something we'll need to discuss as well. And of course, generality. Once we build this thing, how do we evaluate it and understand, can it actually tackle the range of different tasks that we might want it to do for practical utility? So let me start by talking about models, and this is probably the more technically sophisticated part of this talk. I'll keep this pretty high level, but I do think it's worthwhile to understand where the underlying machine learning technology for robotic foundation models actually comes from. So I'll tell you how we can go from large language models to vision language models, which are LLMs that can process image observations, to modern vision language action models, which are essentially advanced LLMs that can also control robotic systems. So a large language model, fundamentally, is a transformer neural network that predicts future text tokens. So roughly speaking, you can think of it as a model that fills in the blanks. So you give it a prefix, and it produces a probable suffix based on what it's been trained on. And this can be actually, although it's a very simple recipe, can be tremendously powerful because it can learn, for example, that if the prefix is a question, then the suffix should be an answer. So large language models really serve two purposes in modern machine learning technology. First, they provide a way to distill huge amounts of knowledge from the web into a single neural network. And second, they can themselves serve as AI assistants or machines that actually answer questions. We're much more interested in the former in this case, because we're not going to be using them as AI assistants. We'll be using them as a foundation of knowledge on top of which to build controllers for robotic systems. Now, LLMs only interpret text. If we want to extend them to also process visual observations, we can build what are called vision language models. Vision language models are classically trained by taking an LLM and then training a separate neural network to embed images into the same representation space as text. So essentially, you have this object, the LLM, that can understand text, and that text is processed into a particular embedding space, a continuous representation of text. With VLMs, with vision language models, images are also embedded into that same space, so that now what used to be a large language model becomes a vision language model that can also interpret images. And this is essentially the basis of how modern robotic multimodal large language models work. Things like Gemini, GPT-5, etc. They're all based on this principle. If we want this thing to also control robots, then we have to further extend it to also modify the outputs. So the outputs of vision language models are still text. If we want them to control robots, we need to add some additional output modality that allows them to output controls for a robotic arm. The first generation of vision language action models, or VLAs, did this fairly naively, simply by treating robotic control as essentially a kind of question answering problem, where the question was the robot's command, like fold a t-shirt, and the answer was a sequence of numbers representing the controls that should be applied to the robotic arm. And this was a reasonable way to transfer the knowledge in LLMs and VLMs to robotic control, but it was not very well suited for highly fluid, high frequency, and dexterous robotic control, because of course, outputting the raw numbers literally as ASCII characters is not a very scalable recipe. So the modern second generation of VLAs essentially mirrors the approach in VLMs. In VLMs, an additional neural network component was added to process images. In second generation VLAs, an additional neural network component is also added to process actions. The way you can think of it is, if the image encoder is a kind of visual cortex, then the action decoder is a kind of motor cortex that is added to the LLM backbone. Typically, this component is trained with some variant of diffusion or flow matching, because these machine learning techniques are more well suited for processing continuous distributions. And of course, robotic controls are continuous values rather than discrete values like text. But if you want the high-level summary, essentially, the VLA recipe, the second generation VLA recipe, grafts a kind of motor cortex onto the LLM backbone in the same way that the vision language model grafts a visual cortex onto the LLM backbone. So second generation VLAs add a dedicated continuous output mechanism that can specialize for motor control. So one example of a second generation VLA was the model that performed the laundry folding task that you saw in the video in the beginning. This was a model called Pi0. Pi0 was actually the first second generation VLA, which processes multiple images, feeds them into an LLM backbone, and then decodes continuous actions using flow matching, which is a variant of diffusion. Now, since then, VLAs have progressed quite a bit. So this was about a year ago. Before they would process image inputs and language commands and output continuous actions. Modern VLAs, like the Pi05 model, which was the model that was used in the second video where you saw the robot cleaning the kitchen, add additional mechanisms to better capture the semantics of the task. Because once you have sufficiently capable low-level motor control, then the next bottleneck becomes to understand the semantics of the scene and produce an internal plan that allows you to rationally decide how to act in the desired environment. So the Pi05 model integrates high-level reasoning with low-level control. The pre-training for Pi05 follows a kind of a standard paradigm with next token prediction, but now the pre-training data contains data from many different modalities: text, images, bounding box, and other computer vision tasks from the web, as well as robotic tasks with actions discretized into a specialized tokenization. And this is just used to train the model to understand all those modalities. And then there's a post-training phase that actually integrates two new components: this motor cortex like before, and an additional mechanism for high-level reasoning. So you can think of this high-level reasoning as analogous to chain of thought, or the kind of thinking that modern thinking models like GPT-5 and Gemini perform, where the model will actually observe the scene and accept the user's command, like clean the bedroom, and instead of directly producing actions, the model will actually produce predictions about intermediate steps that it could take. And these are produced in text. So these are semantic steps, like if I need to clean the bedroom in this environment, I should pick up the pillow. And essentially the model talks to itself. It says that to do this, I need to pick up the pillow. And when it drills down to the lowest level, then it says, okay, now I figured out the low-level behavior. I should send it off to my action expert, which is my motor cortex, and tell it to convert that behavior, like pick up the pillow, into continuous actions. And this is roughly the architecture that many modern vision language action models follow, where they plan how to perform the task semantically in text, and then ground it in low-level actions through some kind of dedicated action expert. Now, of course, this is just the design of the neural network. In order to make all of this work, we need to train it on the right kind of data. And as we know from other areas like NLP and computer vision, data is absolutely crucial for the performance of these systems. Data is every bit as important as the design of the neural network itself. The original Pi0 model that we developed about a year ago was trained on data from 7 different robotic systems where we collected data in our own laboratory, as well as data sourced from the internet. And data from the web included open source robotics data sets, as well as data sets that were not designed specifically for robots, but could serve to endow the model with visual and language understanding. From there, the model could be used in different ways. After training on this diverse data set, it could be used directly to control a robot, but it could also be adapted to specific difficult downstream tasks with high-quality post-training data. And again, this very much mirrors the kind of training procedure that is typically used for LLMs, which have a pre-training and a post-training phase. The purpose of the pre-training phase is to endow the model with broad knowledge and understanding. The purpose of the post-training phase is to tell the model what you want it to do. So essentially, pre-training is like learning all the knowledge. Post-training is like say, okay, now that you have that knowledge, here's how you use it to actually solve the problems that users want solved. And post-training on high-quality data can enable specialized policies that can be very proficient at very difficult tasks like folding laundry, or if the task is simpler, then perhaps small amounts of data can be used to very efficiently post-train to new tasks or even new robotic platforms. So here is a particular illustration of the specifics for the Pi0 model. This is the model that's from about a year ago. The pre-training data for this model had about 10,000 hours of robot data, very diverse data from many different robots, typically not very proficient behaviors. So there was a mixture of good and bad data. And the purpose is to illustrate the range of different situations that the robot might need to handle. The post-training data was typically much more narrow, on the order of tens of hours for tasks like folding laundry or building a box, focusing on the specific, highly proficient behaviors that the robot should exhibit to perform these tasks correctly. So post-training is high quality but narrow data, which illustrates consistent strategies to perform a task well. By itself, training on only this good data doesn't work because when the robot makes mistakes, it'll encounter very unusual situations which are rarely seen in the narrow post-training data. But if it is pre-trained on diverse data, that pre-training data actually covers that range of situations and tells the robot how it should recover. So here's an example of Pi0 being fine-tuned to a new task that was not present in pre-training. The task is to pick up a flattened cardboard box and assemble it so that it's fully built. Here you can see Suraj Nair, who's one of the researchers on this project. He drops the unfolded box in front of the robot, and then the robot begins folding it. This is a very complex behavior because you'll actually see that the robot makes a number of mistakes. Sometimes it misgrasps or doesn't fold correctly and has to recover from that. It's also physically very challenging because you have to brace the box against the table in order to fold it correctly. So these are the kinds of behaviors that are essentially impossible to do without machine learning. Traditional robotic motion planning methods would not be able to handle this, both because of the challenge of modeling the deformable box and because of the physical complexity and the contact dynamics required to perform this task. The task, of course, works in a variety of initial conditions, and since this original work, which was about a year ago, we've improved the policies so that they perform this much more proficiently. Here's another task. This is folding laundry. Here the robot takes clothing items out of a basket and folds them, and it can fold different clothing items. It can fold them into a stack where there's multiple items present. You can also do this with different robot platforms. So here you can see in the bottom, there's a mobile robot that's standing in front of the table. And it's not perfect, like it sometimes makes mistakes, but critically, because it has that pre-training and post-training recipe, the model is actually taught how to recover from mistakes when it makes them. And it can do other things with clothing, like take them out of a dryer. So the reason we selected this task is because the variability present for these kinds of tasks is enormous. Unlike tasks that robots might do in a factory where the initial conditions are tightly controlled, in this case, the initial configuration of the clothing items can be extremely diverse, which means that the robot really needs a generalizable policy to handle all the different configurations that these items might get into. One of the really interesting things about this kind of recipe is its ability to learn recoveries from perturbations. So this was not something that we really planned for, but after we trained this model, we experimented with perturbing in various ways. So here you can see that Michael throws another clothing item on the table while the robot is trying to fold the shorts, and the robot figures out that it needs to put it back in the bin. This was not something that we intended for the model to do, but in the course of learning from large amounts of diverse data, the model actually acquires these kind of behaviors in much the same way that LLMs acquire emergent capabilities. And here are some more examples of perturbations where Michael will go in and mess with the robot, and you can see that in each case, the robot does something sensible to recover from that perturbation. And this is really, really important for deployment of robots in real-world settings, because of course, in open world settings like the home or a hospital or an office building, unexpected things will always happen. And while it might be impossible to have a robot that never makes mistakes, if you have a robot that can correct its mistakes and recover from them, then you can actually handle those kinds of situations. Now, I mentioned that Pi 0 was kind of the earlier prototype of the system, and the newer version, Pi 05, integrates a kind of a thinking mode, a reasoning mode that reasons about more complex tasks. And this enables the newer models to handle much more temporally extended problems. So in this video, you can see the Pi 05 model cleaning a bedroom. This is a much more temporally extended task, depending on how many items there are. This can take between 10 minutes to as much as half an hour. You have to put all the laundry items away into a basket. Then it might need to put away the trash and make the bed. And this kind of stuff requires the model to have that high-level reasoning to plan through what it's doing. One of the really interesting things about this video is that this test is being conducted in a home that was never seen in the training data. This is, of course, exactly what we would want from generalist robots, but it's something that up until this work was actually not something that had been done successfully. So as I mentioned, the main thing that distinguishes this model from the previous one is its ability to keep track of longer horizon behaviors by having those internal thoughts in language about what the intermediate stages of the task should be. Now, one interesting thing about the Pi 05 model is that while we evaluated on controlling mobile robots like the one you see in this video, the training data actually, to a very large extent, consisted of data from static robots, because mobile robots are comparatively more expensive. It's harder to collect data on them. So this image illustrates the data mix used for Pi 05. I won't go through all the details of the data mix, but it involves many different data sources, including non-robot data from the web and data from many different robot types. But the interesting thing is that the mobile robots, which were the ones that we actually used to test this model, constituted only 3% of the entire data set. And I think there's something important to take note of here, which is that unlike in the classic paradigm of robotic learning, where typically the data is collected directly on the platform that is going to be deployed, with robotic foundation models that are trained on very diverse data sets, it's actually possible to onboard a new platform, including an entirely new type of platform like this mobile robot, with a very small amount of data, because the broad data that is present to pre-train the model already gives it a fairly good understanding of physical interactions. So with only 3% of the data comprising data from these mobile robots, the robot's actually able to acquire fairly broad skills. And here are a few more illustrations of these mobile robotic platforms in different homes being tested on a variety of different skills. So in the top left, you can see the robot folding a towel in the kitchen. In the top right, you can see that it's cleaning up a kitchen. In the lower left, it's cleaning up a bedroom where some people go in and kind of perturb it, again, to test its robustness to perturbations. One of the interesting things that we found with the Pi 05 model is that once the model acquired a sufficiently sophisticated understanding of physical interactions, it could be improved further with only higher level supervision. So one of the things that we did is we incorporated this data that we called verbal instructions. Essentially, when the robot went into an environment where it was not successful, we could go in and simply tell it how to do the task step by step. So to say, well, to clean up this kitchen, first you close the microwave, then you pick up the plate, then you put that in the sink. And this sequence of verbal instructions was actually often enough to get the robot to succeed in a novel home where it would otherwise fail. And furthermore, when we took those verbal instructions and included them in the training data, that actually improved the robot's performance in novel homes without any additional action supervision. And this is really interesting because what it indicates is that once the model is sufficiently good at physical interaction, it can improve further only through high-level supervision in the form of instructions. Much like a person might get better at a skill by being coached through it in words. So this is pretty interesting because, again, what it shows is the power of having robotic foundation models. Because once you have these foundation models with diverse skills, even the ability to improve them further is easier because they can process this high-level supervision. Okay, so I talked about models and data, and these are really the key ingredients that go into making these things work. But how broadly do these things generalize? So one of the things that we want to understand with Pi-O5 is the potential for Pi-O5 to generalize to entirely new homes. So we trained it in a number of different locations. These were homes around the San Francisco area. We had 100 locations in total. And then we tested the performance of some of these tasks in novel environments, so entirely new homes that were not seen in training. This graph shows the performance of the model after training on different numbers of locations. And you can see that performance starts to plateau somewhere around 60 to 100 homes. When it gets to 100 homes, it's about 80% success rate, which, by the way, is not that high. I think there's more work to be done to get this number higher. But of course, the important question here is, how close is this success rate, this generalization number, to what we would get if we actually trained directly in the deployment location? So the upper bound for this is not necessarily 100% because there are other technological limitations to the system. The upper bound is what would happen if we trained directly in the test home. And that's shown by this green bar. So the green bar is a baseline where we directly collected data in the evaluation environment and trained on that. And you can see that the yellow curve, which is not trained in the test environment, actually matches the performance within the confidence interval of a model that was trained directly in the test environment. So that means that when it comes to generalization, when it comes to ability to generalize across different homes, the generalization ability is actually maxing out here. Of course, it kind of opens the next question, which is, well, how do we go from 80% to 100%? And that's something that I'll talk about towards the end of this talk. But it does suggest that in terms of generalization capability, the number of locations required is quite reasonable. Now, the other thing that we measured here is what would happen if we do the same experiment, but without using the general purpose robotic foundation model as initialization. So what if we train on only the mobile robot data in these different homes? And that's actually quite a bit worse. So even if we cheat and train directly in the test environment, if we don't use the foundation model initialization, that's shown by this light green bar, the performance is half of what we would have gotten if we used the foundation model. And if we used only the training homes without training on the test home and did not use the robotic foundation model initialization, then performance is extremely poor. So this is showing that, yes, generalization capability matches what we get from in-domain training, but only if we actually use the robotic foundation model that is trained on that diverse data set from many different robotic platforms in many different locations. We also measured the marginal gains from the high-level inference, from the thoughts inside the Pi-O5 model, these semantic inferences. This bears a little bit of explanation because there are many different methods being compared here. But to briefly summarize, the leftmost bar shown in yellow is the complete Pi-O5 model. The acronym HL stands for including high-level data in training. So this is basic semantic data that pairs images with robotic commands. VI is the verbal instruction data. So this is that additional data where we walk the robot through a task. And WD is web data. So data sourced from the web for things like image captioning and visual question answer. And the different bars to the right of the yellow bar are essentially ablations of the model where we take out certain components. So no HL means we take out high-level instructions. No VI means we take out the verbal instructions where we walk the robot through a task. And no WD means no web data. And you can see that each of these ablations degrades the model's performance quite significantly. An interesting baseline is the second bar from the left, shown in light green, which is labeled as implicit HL. This is essentially a model that is trained on the same exact data mix, but doesn't actually perform the thinking at test time. So it's basically trained to think, but then asked not to think at test time. And interestingly, this is the second best model, which means that much of the benefit is actually derived simply from including all of those verbal commands in training, even if they are not used at test time. Of course, if you use them at test time, then it's even better, but this shows that really the model understands those semantics and transfers the knowledge from them. Another interesting experiment that I want to share with you is some of the work we've done on adapting these models to other robotic platforms. So this is a video from a company called Astrobot, which develops humanoid robots. And the experiment we did with Astrobot is we actually fine-tuned the Pi0 model to the Astrobot robot using a modest amount of data from this robotic platform. And even though this robot is completely different from anything seen in the model's pre-training data, the robot was still able to perform fairly sophisticated tasks. And I think this video nicely illustrates some of the potential of robotic foundation models to enable widespread deployment of robotic systems, where even if the model is not pre-trained on the robot in question, it could be adapted to new robotic platforms, enabling other companies to innovate on robotic hardware and quickly get controllers for that hardware by adapting pre-trained robotic foundation models. Now, in the last few minutes of this talk, what I want to also tell you about a little bit is some of the technologies that are on the horizon for robotic foundation models. One of the things I mentioned is that even with the Pi05 model, the actual absolute performance is pretty good, but it's not quite yet at the level that we would want from a practically deployed robotic system. So what are some of the things that can help us bridge that last mile? Well, to help us understand this, what we can do is we can put side by side the anatomy of how regular foundation models are trained versus how robotic foundation models might be trained. The recipe for regular foundation models like LLMs and VLMs is actually pretty well defined at this point. It consists of a pre-training phase that uses diverse data from the web, and a post-training or alignment phase, which uses supervised fine-tuning on high-quality data, and very often now reinforcement learning, either reinforcement learning from human feedback or more often reinforcement learning with verifiers to help the model achieve the best performance. And we could imagine that in the future, the same kind of approach might also be practical for robotic foundation models, where they might be pre-trained on very diverse data and then post-trained both on high-quality demonstration data and with reinforcement learning to help them achieve the highest level of performance. And while training VLAs with reinforcement learning remains kind of at the cutting edge of current research, the reinforcement learning algorithms have actually become very sophisticated. I'll share with you some results from some recent experiments that we've done with reinforcement learning. Here on the left, you can see a video of a robot learning to insert a chip into a PCB board. This is actually showing the learning process in real time, starting from a few demonstrations. And you can see that in the first few minutes, the robot generally fails at the task. But as learning progresses, you'll see that it gradually, right in front of your eyes, will learn to insert the chip more and more. So already you can see that it often inserts the chip into the PCB board, and after about 10 minutes, it can do this consistently. Of course, once it's learned that skill, then you can use it as much as you want. This is really interesting because reinforcement learning from visual observations typically is considered to be a very expensive technology, something that needs to be done in simulators for millions and millions of trials. But modern reinforcement learning methods, in this case, this is a method called SERL, can learn this task in just tens of minutes. There are a number of things that make this possible. Advances in reinforcement learning algorithms are one big one. Other things that make it more efficient are things like incorporating human-in-the-loop interventions. So here on the right, you can see a video of two Franka robots learning to put a timing belt on some gears. When the screen turns red, there's an expert intervention where an expert user actually modifies the behavior to teach the robot in real time how to correct mistakes. And these additional corrections are incorporated into reinforcement learning. So the robot doesn't just blindly imitate them, but it uses them as a kind of a coaching to help it improve its behavior. Here are some videos of the kinds of behaviors that reinforcement learning algorithms can learn. And you can see that there are a variety of different skills here. On the left, in the top, the robot is attaching the timing belt. In the lower right is a very dynamic skill where the robot needs to use a whip to remove a Jenga block from a tower. The tower is not glued together. It's like an actual tower. It's being held only by friction, so it needs to be very delicate and precise in hitting exactly the right block. In the lower left, you can see it flipping an egg. In the upper right, you can see it helping a person assemble IKEA furniture. All right, so a few closing thoughts and perspectives before we move into the Q&A. Robotic foundation models, I think, can be an essential tool to make generalist robotic systems practical. Uh, Now, to make these systems a reality, we need to develop the right technologies, the right models and algorithms, but we also need to bootstrap them with data. And creating the kind of data that would enable the next generation of robotic foundation models is also a pretty major challenge. The generality of these models is important. One of the things that I showed in some of my experiments is that the foundation model initialization is actually an essential component to getting the generalization that we want. So in this graph, for example, we showed that yes, we can match the performance of what you would get if you were to actually train directly in the test environment, but only if you use the robotic foundation model initialization. So you really need that broad basis of data rather than just building narrowly specialized systems. On the other hand, maybe some of the good news here is that the real-world generalization is perhaps closer than one might think, because we can already get these systems to generalize to entirely new homes. But of course, a lot more research needs to be done to improve their performance, to get them really to 99.999% reliability, to develop methods for these systems to solve very complex and long horizon tasks, and to get them to learn more effectively from human feedback and human intervention. All right, I'll stop here and I'd be happy to take questions.
Oh, thank you. Thank you so much, Sergey, for such insightful presentation. So now we would really like to hear from the audience. So if you have any questions, please type them into the AI for Good neural network chat room, and we'll take many as we can during this Q&A segment. So we have already a few questions coming in. So the first one is, what's your views on observability in VLAs? How can you know if them are working as intended on a robot?
Yeah, this is a very subtle question. So generally, I think it's very difficult to build machine learning systems that right off the bat are guaranteed to work in every setting. In fact, it's difficult to build any kind of system that is intended to control an autonomous robot in diverse environments and guarantee that it will always work. What I think we should strive towards is to build systems that have two essential ingredients. One is common sense understanding, and that comes from this high-level semantic reasoning, which means that if something unexpected happens, the model should at least understand that there is something strange going on and react in a semantically sensible way. So if you tell if the robot is folding the laundry and a cat sits on the table, maybe the robot doesn't know how to handle that. Maybe it cannot succeed at its task, but it should at least understand that something unusual is happening and know that it should stop, it should wait for the situation to resolve or do something reasonable. I think that foundation models give us a really powerful tool for this because they have a good visual understanding of the world. So if you give a picture of a table with a cat on it and you ask, Gemini or GPT-5, like, what should the robot do in this situation? It'll probably tell you something reasonably sane. So if we can transfer that knowledge into the robotic systems, which we do with VLAs, then we can get that level of robustness through common sense. The second thing, and this is more towards actually succeeding at the task, is that we need to build systems that can learn from their mistakes and become better. And this is where reinforcement learning technology is so essential, which means that while you might not get a system that can entirely in zero shot succeed 100% of the time in a target environment, when it does make mistakes, it should be able to incorporate them into training and get better. This is a very difficult problem. It is still at the forefront of current research, but reinforcement learning technology, I think, can get us there if we can generalize it to this setting.
Okay, thank you, Sergey. So we have questions keep coming. So how can we train on human data instead of robotic training samples? There might be a need for a layer to replicate human actions into robot actions.
Yeah, this is a really good question. And this is, for context for everybody else, this is something that researchers in robotics have been very concerned with for a very long time, which is that, well, if robotic data might not be as plentiful, whereas videos of people might be much easier to get, how do we properly incorporate videos of people into robotic learning? This is a complex question. My own opinion on it is the following, that I think it's very difficult to build robotic learning systems that operate entirely on videos of humans. Even a person wouldn't be able to do that, right? Like imagine that you want to become better at playing tennis, and instead of practicing tennis, all you do is you watch tennis on television. You might learn something about the structure of the task. You might learn that, oh, these are the strategies I should use, but you're not going to become an expert tennis player just by watching it. However, if you play tennis and you practice and then you watch it on television, now you can put those different sources of information together and become better. So I think the key to utilizing videos of humans in robotic learning systems is again to build very good robotic foundation models, which establish that foundation using robotic data, and then on top of that, they can better utilize videos of humans as well for supervision in the same way that you as the tennis player can learn from watching tennis once you already have that basis of grounded knowledge from your own practice. So basically the message I would have here is let's build really good foundation models because on top of that, it'll be better to use these other sources of supervision.
All right. So moving to our next question. So we have how are you, for example, experimented with VLAs for outdoor navigation applications?
Yeah, that's a really good question. So in this talk, I described experiments that are entirely focused on manipulation. The reason being that manipulation is probably one of the toughest frontiers in modern robotics, where for things like folding laundry, there just aren't like good alternative methods. But we have also experimented with VLAs for navigation. They work very well in that setting. One of the really exciting things about VLA models for navigation is that you can endow them with much richer language following capability than you would get naively. In fact, we can actually take data sets for navigation from domains like driving and sidewalk robots, even without any human-provided language labels, label them synthetically with existing VLMs like Gemini and GPT-5, and fine-tune VLA models to them, and you'll actually get pretty sophisticated language following performance. A recent work from my academic lab at UC Berkeley on this, authored by Noriaki Hirose, is called Omni VLA. Those of you that are interested in VLAs for navigation, I would encourage you to check it out. It has some pretty nice results. There are many others, many other works in this area. There's some work from NVIDIA called Navila that's also very interesting. So it's a very active area of research.
Thank you. Thank you for your answer, Professor. We would like to ask you as well, how do you specify the end of a task? Do you include that information in the training data? And if so, how do you do that?
Yeah, so I think it's not something that has been done in a very sophisticated way so far. For all of the tasks that I showed in this presentation, actually, the robot is simply trained to put the arms back into a rest position when it finishes the task. And there's nothing in the model that explicitly detects it. It just, because the data has the arms going back to the rest position at the end, that's what it does. But this is not really like a good general solution because in a realistic deployment, the robot might be asked to do many things. So it needs to understand when it finishes something and then move on to the next task. This is something that can be done by leveraging that same high-level reasoning mechanism. So in the same way that the high-level reasoning process outputs semantic steps, it can also evaluate its own steps. And that's something we've experimented with. We don't have any published work on this yet, but it's something that's in the pipeline.
Okay, thank you for this. And how do you think that the robot can learn across different domains, fixed, mobile, aerial, marine? How this is going to be possible through the foundation models?
So initially, when we started working on cross-embodiment systems, this was maybe three years back or so, starting with the RTX project, we thought that we needed to develop specialized systems and specialized neural network architectures to handle the different embodiments. But what we actually found over the last couple of years is that even very naive approaches tend to actually work fairly well here. It's a little bit surprising, but maybe makes sense in hindsight because in the same way that neural networks can generalize over different environments and different objects, they can also generalize over different robot embodiments. So the Pi 0 and Pi O 5 model, they don't actually do anything clever. They simply concatenate all of the actions from the robot into a single vector, pad it with zeros for any actions that don't exist, and feed them into the model. I'm sure that there is more sophisticated work to be done in terms of decomposing the action space in semantically relevant ways, but so far we haven't found that to actually be a significant obstacle.
Okay. And we have as well a question on long horizon tasks are generally non-Markovian, and I have observed that my robot gets confused when it faces such observations. How do you think VLAS can deal with it?
This is a very sophisticated question. So, um, For a bit of context, something I should mention, maybe by way of a confession, is that all of the policies that I showed in this talk have no memory, meaning that they observe the current time step and they don't actually keep track of how they got there. Incorporating memory into robotic policies has actually been a significant challenge. There are ways to do it, and it's definitely not impossible, but one of the things that makes it hard is that there's basically, when we deploy a learned system into a control setting, one of the biggest challenges we have to contend with at the technical level is something called distributional shift. Distributional shift means that the distribution of inputs into the model seen during training doesn't match what is seen during deployment. Why doesn't it match? Well, it doesn't match because during deployment, the robot is choosing its own actions, and therefore it encounters states that might not have been seen in training because in training those mistakes weren't present. Incorporating memory exacerbates this problem because when you incorporate memory, now you're vulnerable to distribution shift at the level of the single observation and at the level of a history. And there are many more ways to experience distributional shift at the level of histories. So because of this, using history, using memory, actually makes it harder to get robotic policies that generalize successfully. This is an open area of research right now. There have been very good ideas put forward in this area, but it's still an ongoing area of research where I don't think the community has fully figured out how to get memory into robotic systems successfully while mitigating this problem. I think we'll figure it out. I think this is something that's, maybe we'll make a lot of progress on that even this year or next year, but it's still an open question.
Thank you. Thank you for this. I think there is a lot of interest from our audience, and we have another question on 3D semantic understanding. Do you think that 3D semantic understanding is key to the robotic application using some foundation, for example, knowledge base of this Earth in 3D models? Human beings and most animals, well, have two eyes to form 3D recognition of this world.
It's a really interesting question. I think this question gets to the heart of a very long-standing debate in machine learning, which is the degree to which understanding in learned models is emergent or comes from human-specified inductive biases. So it may very well be that the current models that I showed already have implicit 3D understanding because they learn how to act in the world using multiple camera views. So all the policies that I showed, they use three camera views, one on each wrist and one on the base, which in principle is enough to deduce 3D structure. But nothing in the training of the model itself or the design of the architecture actually encodes 3D structure. So perhaps it is emergent, perhaps it isn't. The debate in the ML community is between whether is when we know that some piece of structure is important, do we try to manually encode it in the system, or do we provide it with a kind of data that can allow the system to understand it on its own? And this is a very complex debate. So if you want to learn more about kind of some of the philosophy of this, I would encourage you to check out Richard Sutton's essay called A Bitter Lesson, which discusses perhaps some of the reasons why we might not want to bake in certain kinds of structure. But of course, every rule has its exceptions. For example, in computer vision, convolutional neural networks were very successful for many years, and arguably convolutional neural networks do bake in a certain kind of invariance. So is the structure of the 3D world something that should be baked into networks as an invariance or not? I don't know, but I think it's not something that's actually extremely clear-cut because sometimes letting a network figure it out for itself while providing with necessary data can work better than specifying it manually.
Thank you for this. We have another question on your thoughts on research directions, feasibility and practical uses for small language models to the physical world, like the recent tiny recursion models, with the goal of really reducing this barrier to entry and spur more innovation.
Yeah, this is interesting. So I don't know. What I'll say is this. I think that even if you want to do research on sort of industrial scale models, even if you work at a very well-resourced company, being able to iterate quickly is tremendously important. So I think that being able to work with small models and derive scientifically relevant and statistically significant answers is essential for progress in the field. So whether we care about accessibility and democratization of science, or whether we simply care about making progress and are not as concerned about resource limitations, understanding how to use small models to derive actionable conclusions and conclusions that hold even at a large scale is really, really important. The main reason why scaling laws made such a big impact on the study of foundation models is exactly this, because it was a tool that allowed researchers to deduce answers from small scale and use those answers at a large scale. So now the question here is, of course, whether for the strongest production quality systems, whether we will see smaller and smaller models achieving that kind of capability, or whether it'll still remain the case that small models are more for rapid iteration, and then when we want to deploy something in production, then we want to go with the largest model. I don't know the answer to this, and recent research has indicated positive signs both ways. So we've seen smaller models become extremely capable, but we've also seen larger and larger models get even more capable. So I don't know which way it'll go. But in some ways, maybe we don't have to figure that out. Maybe we need to get good at using small models anyway, because that's how we do rapid research and make progress. And if they end up being just as strong in the long run, even better.
Okay, thank you. Thank you for this, Professor. What is your opinion on using the same vision language action models for both navigation as well as manipulation tasks?
This is a very, very interesting question. So we had a study that we did a couple of years back. And this was actually a study led by Jonathan Yang at Stanford University, where we actually examined exactly this question, where we took data from robotic navigation settings, things like sidewalk robots and autonomous vehicles, as well as data from robotic arms. And we systematically examined whether combining both sources of supervision actually improved performance. And we found that actually it did make a big difference. It was successful in improving transfer for the case of manipulation tasks that involve visual servoing. So anytime you're grasping an object, you're basically doing a visual servoing task where you need to move the gripper towards an object. And navigation data was actually really helpful in improving the generalization of that. It kind of makes sense because navigation data tends to be much broader. So when you have a mobile robot, it sees much more of the world. And the basic pattern that you can learn from that kind of data is essentially how movement through space is affected by your actions. So if you want to do better visual servoing, an improved understanding of that is very helpful. Now, I think it remains to be seen whether this kind of transfer goes beyond just visual servoing. Like, can you learn something about physical interactions as well? I don't know. That's a lot less clear cut. And I think that's an area for future study.
Okay, thank you for this, Professor. And another question is about how do you deal with different types of tasks, fast versus slow tasks. Some tasks, of course, others require reflex response. How can VLAs achieve that?
So far, I haven't seen systems that perform adaptive reasoning, but I do think that that would be the natural next step. So the experiments that I showed, the high-level reasoning is performed simply at a fixed time interval. So I think it's like every 2 seconds, the robot will generate a new semantic command. But you're completely right that for tasks that require, for example, fast reactions, it might be necessary for the model to dynamically decide when to think harder versus when to rely on a quick reaction. I would imagine that similar kinds of ideas as the ones that have been used for LLMs to determine adaptively how much to think could also be applied here. I think it's a very interesting area. There are lots of tasks where you would want fast reactions like that, but I think this is still at the forefront of current research.
Thank you for this, Professor. Another question is, what about the limitations of foundation models in perceiving small objects relevant to fine manipulation tasks, such as screws and needles?
Yeah, this is actually kind of tricky. So I don't have a particular answer for you technically, but one piece of evidence that I could share with you is that when we were conducting this research, our models are based on existing open source VLMs, and these use pre-trained image encoders. Traditionally, image encoders for VLMs are trained with some variant of a self-supervised objective or a semantic clip objective. Traditionally, people that work on VLMs find that while it can be helpful to fine-tune these vision encoders, oftentimes the vision encoders trained with self-supervised learning or clip are already very good for a lot of tasks that are semantic, that occur in these benchmarks like BQA and image caption. For the robotic tasks, we actually found that it was absolutely essential to fine-tune the encoder end-to-end, in contrast to the experience that computer vision researchers have. So to me, this piece of evidence actually suggests that spatial understanding in these vision encoders is not quite at the level that is necessary for sophisticated robotic control, and perhaps this problem with small objects is one instance of that. Now, in terms of how that could be addressed in the future, there's always kind of the brute force approach of handling higher and higher resolution images. I think in our case, wrist-mounted cameras actually help a lot. Like, it's a little bit of a hardware hack, but it does make a big difference. There might also be more sophisticated methods like foveation that could be developed in the future. But maybe the one thing that I could say concretely is that probably the vision encoders that are developed in computer vision for semantic tasks are not quite optimal for these robotic problems.
Okay, thank you. Thank you for this. We would like to ask you as well about the enormous computational resources that these large models require. And what are your thoughts on balancing these innovations with sustainability in robotic foundation model training?
Yeah, this is a complex question. I don't think I have any particularly clever answer to this. I think that it's a challenge, and it's particularly a challenge when we also factor in not just the cost of running inference, but also the cost of R&D. Because while for a production-ready system, perhaps the cost you pay is just to have the model running, and that's kind of something that you can calculate in advance. R&D requires iterating through many different model designs, and that also requires enormous computational resources. I think it's a challenge. I don't think that the robotic problem makes that any easier. If anything, it makes it harder because robotics is a very multimodal problem, which requires more complex systems, more complex training procedures, and things like that. Yeah, so it's a challenge. I think it's a challenge we should think about very carefully, and I don't think I have any tools that make that challenge less of a challenge, unfortunately.
Well, there are many questions from our audience, but we know that you have very limited time, Sergey. So probably we will need to be taking the last questions. I think we wanted to ask you, what are, let's say, if you would like to highlight one of the next breakthroughs that you think that is going to really enable these future real human robot collaboration in real time in the real world. Like, you are working on this like really every day, and well, all our audience, many researchers, it's about this conversation. When are we gonna see what are the next breakthroughs to really have these robots collaborate with us in real life?
Yeah, that's a good question. I think one of the most important next steps that I would anticipate in this area is robust and reliable algorithms that enable robots to improve directly on the job. I think that the beginnings of these methods already exist, but so far, in terms of the systems, in terms of methods for training the largest systems, like the Pi 0 and Pi O5 models, they still very heavily rely on very rigid supervision in the form of low-level actions. When we get very good at utilizing natural supervision, supervision from outcomes, supervision from human feedback, supervision from language, from someone talking to the robot, then I think we will move on to the next phase of robot deployment, where robots will get better the more they're used. I think many of the pieces for that are falling into place now, but I think that there's still an open challenge there. The reason this is so important is that once robots get better through deployment, through experience that they gain themselves, we will start to see more and more robots around us. And when that happens, then increasingly, the robots themselves will become the predominant source of training data. So it may be that years from now, we'll look back on the early 2020s and think, isn't it strange that AI systems used to be trained on data from the internet? When there are so many embodied systems that are continuously collecting data of the real world as it really is, of the physical world, the physical interaction, vision, human interaction, and that's a much richer source of supervision for them than what people happen to have put on the internet in the early 21st century. And I think that's a future that's coming, and I think it'll be really exciting.
Well, thanks a lot, truly, Sergey. It was a pleasure to have you with us and share your thoughts on our robotic foundation models. We are very happy. There are many questions coming in still, so you can always have access to them on our neural network platform. Just it's always gonna remain there. as well, like for our audience. And we would like really to, we look forward to welcoming you to our upcoming events in the AI and Robotics Discovery series, which continue to explore how AI and robotics can help solve some of the humanity's greatest challenges. And you can find the full program and register for future sessions on the AI for Good website. And again, an open invitation for you and our audience to join us at the upcoming AI for Good Global Summit 2026 from the 7th to the 10th of July next year. One of the main topics is going to be embodied AI and robotic systems. So, Professor, you are more than invited to join us as well as a speaker there. I think it's going to be really, really relevant for our audience. And thank you again for your participation in today's session. Thank you very much.
And thank you all for your attention and your insightful questions.
Thank you, Professor.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.